Good. I just stretched, I just breathed, I feel good. We're back in the YouTube studios for Yay Maths, new edition, new generation, next flabbergation, and next concentration of math videos. Surrounded by studio lights and my good friend Zach behind the camera. We're going to be talking about linear programming, which is really weird for a lot of people because it doesn't make sense about what it is it's trying to accomplish. So we're going to talk about what it is we're trying to accomplish, and then we'll give you two problems to accentuate those goals, okay? Basically, this is the idea. If you have like a graph here, imagine, and if you had certain lines, you know, if you had this line and you had this line, for example, and you had maybe lines even down here and here, okay, and those lines involved shading, what would happen is oftentimes that shaded region would be something like this, okay? And what we need to do is analyze all the points of intersection amongst those lines, all right? Those points of intersection are actually indicators about when this area is operating at its best and when this area is operating at its worst. And I took those words very seriously, right? Because this is actually a business model, right? This is a bunch of constraints. There's some information here about how many cars or trucks you can produce for a day. That's the problem we're going to do today. Or how many acres of land that you can actually, you know, work through every day. And there's certain constraints about it. By the way, here, yeah, you can't work negative acres of land. So that would mean you have to shade up from the zero line and things like that. So if you find these points of intersection and apply them to some sort of profit logic, you could actually determine the best way to run your business. So it's kind of interesting to see that within the lines and the data points of intersection, you can find a most profitable model, right? That's basically what linear programming is. So I'm going to give you an algebraic example first, and then the real life example second. Right. So here you have three different constraints. There are three separate lines. And you'll notice that there's inequalities with them, so that involves some degree of shading, okay? So let's actually put them down, see what it looks like. Okay. So we'll start with y is greater than or equal to 2. Here y is equal to 2. Solid line. Greater than or equal to means we'll shade up because y is a measure of up and down. So just keep that in the back of our mind, shading up with this in green. All right. And then we have over here, x is between 1 and 5 inclusive. Here x is 1. Here x is 5. And it's everything between this. All right. You'll notice that when x is a certain number, that's a vertical line, just like when y is a certain number, that's a horizontal line. And we're shading between here. So far within this little H shape that we have here, this is what we're shading, right? Because we said up from green and between -1 and 5, so this. And now we're going to do this one in red. Let's put the red back. So let's do here red. So that's y equals mx plus b. b is the y-intercept over here. That's 3. So we go over here, 3. And we have a slope of 1 over 1. So that's this. And we could do it again. Solid line, because this is or equal to. Put that in. And this is shading y is less than. So if y is a measure of up or down, y is less than would mean shade down. So this is the what's called feasible region. We'll even name it feasible. I always like the sound of that word, like, yeah, it's feasible. Yeah, it's possible. So this is all the possible solutions that would apply to this system, okay? So we're going to take it a step further, and we're going to find all points of intersection. This point, this point, this point, and this point. And the reason that we're finding points of intersection is because these points could either dictate where this region is performing at its best or when it's performing at its worst. Because this basically could represent all the ways to run your business. You could run your business in a variety of solutions. We provide solutions for all forms of entrepreneurs and enterprisers. These are all your solutions for these constraints in your business. So these points that will dictate when you're at your best, okay, or you're at your worst. So what we need to do is find what those points are. So interestingly enough, these blue ones, we know here x is 5, right here, and this is where y was 2. So we have 5, 2 over here. Same with this. Here we know x is 1 and y is still 2. That's cool. Based on our graph, we went, this was 3, 0 for the y-intercept of the red line. Then we went up 1, right 1, okay? So if we went up 1, right 1, we also know that x is still 1. And y went from 3 to 4, so that's 1, 4, okay? And now we could actually do this one algebraically because it's going up, up, and away. The key to this is that knowing that x is still 5 on this blue line. So within this, we know that x is 5, and we just need to know what x's friend is on the red line, this one. So if we wanted to find the y value for an x value of 5, we could simply plug 5 in here, because that's the red line that we're talking about right here. So if we plug 5 into this, we'll see right away that the point of intersection, y becomes 8. So that becomes 5, 8. So those are all the points of intersection. 1, 4, 1, 2, 5, 8, and 5, 2. So these are all potential outcomes of our constraints, outcomes of our equations. And now what we need to do is decide which of these points are the best. So we need more information, okay? The next piece of information is called the profit model. I'll show you what it means. Oh, come on, easily. Stay with it, brother. Stay with it. Oh, profit, that's right here. 3x. I got data all over. I got data at my fingertips and data at my toes. Data's everywhere. It's raining data. So this is basically the way to pronounce this is f of x and y. It's a profit model, okay? It's basically saying this is what your outcome will be for various values of x and y. If you say it's profit, then you want it to be high. And if you say it's loss, you want it to be low, things like that. So let's plug in which of these points would represent the maximum profit and the minimum profit, the highest and the lowest. All right, because these are all potential outcomes of our business model. I hope that makes sense. So let's plug in 1, 2. If we plug in 1, 2, let's go over here. Let's get them all in. 1, 2, 1, 4, 5, 8, and 5, 2. All right. So at this point, I think we're getting warmed up with our algebraic modalities. I don't even know what that means. But we're going to just plug in 1 and 2 for x and y into our profit equation and see which one's the highest and which one's the lowest outcome. So 3 times 1 is 3, minus 2 times 2 is 4. 3 minus 4 is negative 1. All right, let's try 1, 4. 3 times 1 is 3, times 2, or minus 2 times 4. That's 3 minus 2 times 4 is 8. 3 minus 8 is negative 5. Sing with me. All right, well, let's put in 5 and 8 now. So if we do 3 times 5 is 15, minus 2 times 8 is 16. So that's 15 minus 16 is also negative 1. It's a coincidence. And then we go 5 and 2. 3 times 5 is 15. Minus 2 times 2 is 4. 15 minus 4 is 11. So we have a tie for the two minimum values are at points 1, 2, and 5, 8. And the supreme winner here is the 5-2 point with an outcome of 11. So that would represent the max, okay? And what's interesting too is that some problems have clear-cut maximums, maxima and minima, to use the correct phraseology for it. Sometimes there are no maximum and minimum points. So like if I took that out, there was no green line. Get so excited. Still very much a teacher. You guys, wait till you see this. Let's get into it, you know. So you'll notice that there's no minimum at this point. There is a maximum here, the 5-8 wins, or 5-2. Well, it depends. If you put all this in, you know, you could say like 5. It doesn't look like it. Yeah, 5 - 10. In this case, there's no maximum, right? You see that if you plug in 5 - 10, you're going to get something very large. So sometimes the maximum points and sometimes the minimum points don't exist if the region has no bounds, if it's unbounded. But the one we did before with the green line was very much bounded. So if it's bounded, you're going to get some winners and some losers. Let's actually apply this to a real-life problem. Okay, we're back on this. So let's consider this particular problem. There's so many. I thought I had big hands. So suppose this factory is building cars and trucks. I couldn't think of anything more American than building cars and trucks, right? Like watching Fox NFL Sunday. Toyota Tundra is the top in its class of torque and with its appeal and pulls a ship across the nation. And yeah, Ford tough. I just switched brands there, I know. And you got to put in the voice because that's what we're building. We're building trucks. So we're building trucks and cars. Imagine that a certain factory had to put an output of 10 to 20 per day. They were constrained that they had to sell at least 5 each, 5 trucks and 5 cars each. This is the breakdown of what it costs to make a car and sell a car, same with trucks. I made these numbers up, so that if I apologize to anyone in the industry that knows more about this, and if I'm grossly wrong, I do sincerely apologize. But I just thought that maybe, you know, if it costs a car to make $15,000 and you'd sell it for $6,000 more, and then a cost of a truck maybe costs a little more on average to build this truck and then sell it for a little more as well for, looks like $8,000 profit. So per day, what is the maximum profit that we can generate for building cars and trucks? Like how many cars and how many trucks? And so that's the approach to this problem. We have to define the variables. What should X represent, right? And the best way to think of it is like, well, what do I really, really need to know in this problem? What I really need to know is how many of each are we selling? That's really what it's asking. So why don't we let X equal number of cars sold, and naturally Y equals number of trucks sold. So that's how we can frame all our equations. So let's start at the bottom, because we did start at the bottom, now we're here. Started at least 5 of each daily, meaning there must be 5 or more cars made every day, and there must be 5 or more trucks made every day. If you recall what at least means 5 or more. So if you wanted to say 5 or more, that would be the equation X is what 5? At least 5 means greater than or equal to. That's one line that we have to draw. Trucks also at least 5. Okay? So both of these are at least 5. So the next piece that we have to focus on is that we need to make 10 to 20 per day. And if X represents the number of cars sold and Y represents the number of trucks sold, that must mean together that we're making 20 or less in a way, 10 or 20 per day. Because in a way, if you look at it, if X is greater than 5 and Y is greater than 5, you're automatically going to get this 10. It's this 20 is our next sort of constraint, our next bounding, okay? So what you can say is that the number of cars sold plus the number of trucks sold per day must be less than or equal to 20. All right? So together they make 20 or less. Okay? And so let's focus on these 3 lines, just like we did in the previous problem, to create our feasible region, that every possible outcome to our business model. Okay, here it comes. Let's do our outcomes to the business model. Go over here, go over here. Okay, let's hook it up. X is greater than or equal to 5. That is a 1, 2, 3, 4, 5. Hook it up. That is a solid line this way. Shading greater than to the right. Y is greater than or equal to 5. 1, 2, 3, 4, 5. Here's another one. Shading, Y is greater than, shading up. Okay, so we said right from this one and up from this one. So far we are over here. Okay, and the next one is x plus y is greater than or equal to, or excuse me, less than or equal to 20. If you recall our conversation about intercepts, there's a great way to graph this. Let's put it over here. Do you agree that the x-intercept for this line over here is where y is 0? Here, y is 0 here, y is 0 here, y is 0 here. So if we put y is 0, we're going to get the x-intercept. Y is 0, boom, x is 20. Put that in. Same goes the other way around. Like these 2 points exist on the graph, 20, 0, and 0, 20. That's essentially, let's put that like in red. So it pops a bit. That's all the way out here. This is 20, and this is 20. Right? And we come down. Let's say 20 is out here further. Okay? And we're saying less than or equal to, because if y is less than or equal to, once we move the x, we're shading down. Y is less than, we're shading down. So we said right of the x line, up from the y line, and down from red. Here indeed is our feasible region. Okay? And before we continue, it's very important to get the points of intersection. 1, 2, 3. Let's get them. Okay, starting with right here, x is 5, y is 5. That's the point 5, 5. Okay. Let's go up, why not? Here, x is 5. All right, we agreed on that. That's this vertical line. So when x is 5, what's the y value for this red line? That's what we're looking at next. And the y value for the red line, when x is 5, we'll put a 5 in here. So 5 plus what is 20? That's 15. Put that in. So this is 5, 15. And then over here, if you look closely on the horizontal, y is 5. A lot of miles on this board. And y is 5. And so if we put y, 5 over here, right? Put y is 5. If y is 5, 15 plus 5 is 20. It's basically the inverse of that. And that goes over here, 15, 5. Okay? So this basically represents building 5 cars and 5 trucks. This is 15 cars, 5 trucks. This is 5 cars, 15 trucks. Those are the 3 potential ways to conduct our business that may have maximum or minimum impact on our profit. Now let's talk about the profit. That's right here. We'll box this in green because it's green is for money. Boom. There it is. Take this off. And we need our profit model now. That is f of x and y is our profit. Let's talk about it. What is the profit for all cars? Well, if we sell a car at 15, or excuse me, yeah, the cost to make the car, excuse me. The cost to make the car is 15, and the price to sell is 21. Do you agree that is a $6,000 profit for every car? Plus, cost to make a truck, 16K. Cost to sell the truck, 24K. That is 8,000 for every truck. So this represents the profit made on all cars and trucks that we produce within our factory. Okay? Let's see which one works. Well, if we do 5 and 5, that's probably not going to be so much. Let's find the profit on 5, 5. The profit on 5, equals 6 times 5 is 30, plus 8 times 5 is 40. 30 plus 40 is 70. That's $70,000 profit on 5 cars, 5 trucks. Now let's do 15.5 over here. 15.5. All right, 6 times 15 is 90, plus 8 times 5 is 40. So that's 6 times 15 is 90, plus 8 times 5 is 40. 90 plus 40 is $130,000 profit for making 15 cars, 5 trucks. Now let's try the 515, 5 cars, 15 trucks. Here we go. 6 times 5 is 30, plus 8 times 5, or excuse me, 8 times 15. 8 times 15 is the same as 30 times 4, which is 120. So then we have, what was that? 30 plus 120 is 150. And looking right at us. There's our maximum profit. If this factory decided to churn out 5 cars and 15 trucks, they would be making a maximum profit of $150,000 from that particular plan. Which is kind of interesting to put all this to the test and come out with some data. I failed to actually ask for not only the best system for creating the cars and trucks, but actually what would that profit be? And that's right here, the maximum value of $150,000. It's kind of cool. It's kind of cool. Maybe you saw that I was sort of learning it with you along the way, right? I'm still picking this up as I go, and let that be a hope to you, because you know, we're in all in this together, and we're learning about how to profit both in math and in business, and thus as a civilization. All right. Thanks for watching. Yay, math. My homeboy Zach here just had a really important question, and we are free to do as we please. And it's the right question. Why, he asks, are these points potentially going to be the mins or the maxes? All right, because any point potentially within the feasible region could work within our equation. And it's true. Any point within this red region would satisfy all these blue lines. And the answer to that question is all the points at the extreme values are guaranteed to eventually be either high or low. All right, not all points will be high and not all points will be low, but any points that are high or low are guaranteed to be at the extreme values. So that's why we need to pinpoint at them, because these are the ones that are guaranteed to be potential maximum or minimum values. Does that make sense? All right, rock. Okay, thanks. Yeah, math again.